Hello everyone, welcome to AI Anytime channel. In this video, we are going to explore ORPO, which is an acronym for Odds Ratio Performance Optimization. Yet another performance alignment methods for LLM guys. So we have seen earlier performance alignment or alignment methods or techniques like DPO, IPO, KTO, and we also have seen RLHF that has given us chat gpt, that has given the entire world the chat gpt, and all of these performance alignment methods, or in general the aligning the LLMs. We started with RLHF, we have seen DPO, we have seen IPO and multiple other alignments techniques, and they have their own pros and cons. And now we have ORPO, which is a bit different, and we'll talk about that. And we're going to fine tune Mistral 7B instruct the first version of it, zero point 0.1 version. They also have zero point 0.2 they come up with in the last few weeks. And we're gonna take that model, fine tune, align that using ORPO. We're gonna use a dataset, an alignment dataset from Hugging Face H4, and we're gonna perform all of these exercise today in this video. And I will also show you the mathematical intuition, the formulas, a bit of mathematics involved in ORPO, how the objective functions is used, and how it be different. Now, if you talk about a bit on RLHF, right, which is a costly process. Okay, and when OpenAI was working on ChatGPT, they hired human annotators in Kenya. There was a news out, where they says that they have 9 hours per hour or something. I don't know the exact number, but they hire a lot of human annotators who only job is to annotate the data. So they can use that using RLHF. It's a costly process. Not everybody can do that. So don't go into the hype of new bandwagon of generative AI and saying that I can also do RLHF. Not everybody can do that, to be honest. It's requires a lot of it requires vast data sets and a lot of money to do that, by the way. Then we saw, because RLHF has a reward function included into it. It's a reward model, by the way. Okay, function might not be the right word. Okay, so it has a reward model in that they use in RLHF. Then we later on saw DPO coming in, direct performance optimization, and JFR or Jaifer was a great example of that. Okay, that how Mistral were used to with DPO to come up with a better performing model. And in DPO, we had a reference model. So in the processes of DPO, IPO, or KTO, there are two models which are required. So first you will use SFT for generating answers like an instruction, and then you will use a reference model for aligning that. Okay, so if you look at the methods like DPO, IPO, and KTO, they require two model that you do it. But with the ORPO, odds ratio performance optimization, you only one model will do the job. Of course, the data has to be there for that. We will use that for aligning that, and that's the beauty of it. Okay, so we're going to talk about it today in the video, and we're going to perform this in Runpod A100 GPU. I'm going to use Mistral to fine tune it for 100 steps, and we'll see how we can use ORPO for this experimentation. So without any further delay, let's jump into the Runpod and see how we can do that, guys. All right, guys. If you look here on my screen, I have the research paper for ORPO. Okay, which is an acronym for, as we have discussed earlier, odds ratio preference optimization. Okay, and this is a bit different, okay, from the other preference alignments method or the architectures that we have seen. And I've read the research paper. I will recommend you that you also read it. Okay, if you scroll a bit down, if you look at this diagram, I'll make it a bit bigger so you can read this. Okay, or probably from here. Now, ORPO, as you can see, aligns the language model without a reference model. So we're going to talk a bit about why should you use ORPO to basically fine tune, you know, uh, and better align the preferences when it comes to a language model. Now, preference alignment is mainly a process that teaches the AI model or LLMs in general to generate outputs that align with human values or preferences. So you are doing the alignment over there. Okay. So the reason we do it, because we want our AI to be more factual, less biased, or preventing it from generating harmful content. Okay. Now the other methods that we have seen earlier, we started with RLHF, where on the rise of Chat GPT, then we saw DPO, and a lot of other alignment methods that we have seen earlier. So we have seen DPO, IPO, KTO, and blah blah blah. Okay. Now DPO, IPO, and KTO are the alignment methods, and those are cheaper than RLHF, of course, as they don't need a reward model. RLHF is really costly. So if somebody is coming and telling you that okay, we are doing RLHF and trying to become a bit over smart, I mean, I don't know how are they doing it. Okay, so it's a very costly process, by the way. Okay, now DPO and IPO are cheaper. They, of course, they still require to train two different models. So if when you go with direct performance optimization DPO or an IPO, you need two different models, to train. Okay, one model for the, of course, supervised fine tuning, or we call it SFT, and the other model is, to align with human preferences using the SFT model for initialization and as a reference. Okay, now ORPO is just a new method, for LLM alignment. But the good thing about this is that it does not even need the SFT model. With ORPO, the LLM jointly learns to answer instructions and human preferences. That's the beauty of it. And this is again, yet another new method that will have upcoming lot of other models coming in near future. Okay. Now we're gonna see about ORPO. We're gonna fine tune, but also I want to discuss a few things. Okay, about this. Now let me first come here and run this code. I'm on Runpod. As you can see, I'm using A100 GPU, to perform this experimentation of, on Runpod. Okay. Now I'm just trying to see if my tab is open. We would like to also, go through a few things, if that's there. Okay. All right. Now let it install. By the way, we'll discuss about that in a bit. Now, if you look at here on my screen, I have written ORPO. I want to discuss a few things because this might be a bit theoretical, but it's very important for you guys to understand the advantages of ORPO and the results that, they have discussed in the paper, and the conclusion and implementations and things like that, right? Now, imagine if you let's take an example of social media content moderation. If you want to moderate the content on social media, and imagine you are developing an AI system for a social media platform. So the AI is, and we'll give a job to AI. So the AI's job is to automatically generate responses to users' post. So when you just post it, it will automatically generate the responses. However, you want to ensure that the AI responses are not only relevant and engaging, but also respectful and non-toxic. That's where the moderation comes in, aligning with the platform's community guidelines or whatever. Okay. Now, earlier you need two different models, vast data sets that's where we have seen in RLHF and things like that, including both positive and respectful interactions and negative or toxic content. So you need a better labeled data where you have to annotate manually a human annotations, and that's how OpenAI did that when they created ChatGPT. They hired, human annotators sitting in Kenya or in Africa somewhere and paying some hourly rates to annotate the data for the RLHF process. That's how they did it. Okay. Now we're gonna see the impact about ORPO, and how should we do that. Okay. Now I'm just gonna write because it says odds. Okay, let me just change the color here. Okay, I'll just take a. Now it talks about odds. Now let's see if odds, and now let's first talk about a bit of mathematical intuition behind this. Now what I'm saying, the input sequence, given an input sequence X, the model generates an output sequence Y. That's why we're writing Y of X here. If you see this, odds Y. The odds of generating Y are defined uh, as the ratio of the probability of generating Y to the probability of not generating Y. So this is how we basically express that. Then if it's not generating, then it will become 1 minus P and Yx. That's how the formula is. The odds ratio basically for a favored response, that can be YW, over a disfavored response, YL, given the same input X, is the ratio of the odds of generating YW. So this is how we basically then define that. Okay. So we say YW, and then we say YL, and then we write both the odds. So the odds for, and then odds of This is how we basically define that. So this is the key formula for ORPO. If you read the research paper, you'll know. And the objective function. So it basically, the ORPO incorporates this odds ratio into the model's objective function to optimize the preference. And we'll see that when we're writing Optim, when we write Optim, how we dealing with ORPO. When we are fine tuning the code, we'll go through that. Now, basically, it's use a model's objective function to optimize the preference alignment. Now, the objective functions consist of two parts: the SFT loss and the odd ratio loss. So this is how we basically write that. Okay, so I'll just make a bit of change. I'm gonna write LORPO, and that is nothing but LSFT plus LOR. So LSFT is the how should we define? So it's nothing but the uh, I'm probably not write the formula of that, but it's a negative log likelihood loss, used in supervised fine tuning. I'm not going that, you know, deeper, in the mathematical thing and all here, but just to explain, right? And this, you see, this is nothing but the hyperparameter. So this is the hyperparameter that basically controls the relative importance of the odds ratio loss in the objective functions. Okay. Now, this is how you mathematically represent it. Now, so what we are saying that we have a preference definition. So we define the preference when it comes to ORPO. Then the next is probably, you can have an SFT. I'm not saying you can't have. Okay, so and this is what we're gonna use today, SFT with ORPO, and then basically we are eliminating. So when we write eliminating, we're not gonna use a reference model that we used in, for example, DPO. We're gonna not do that here. So I'm just writing eliminating the need for for a reference model. This is what I'm writing over here on my screen. Okay, the it has a lot of real world impacts, guys, to be honest. It basically, it's significant when it comes to resource efficiency, improving the user experience, scalability, and things like that. And they have, this research paper is really good. You should go and read that. Okay, try to understand. They have performed well. The advantages that they offer is that if somebody asks you that why should we use ORPO, or instead DPO or IPO or KKT or whatever, then how will you respond to that? That's the question. Now I'm gonna show how probably in this we're gonna, sorry, not KKO. I said KKO. It's KTO. We're gonna fine tune Mistral in this. Okay, using ORPO. The advantages that you see are, first is of course simplicity. I'm not gonna train twice, so I'm gonna write simplicity. Next I'm gonna write efficiency, and then I'm going to write effectiveness. So these are the three main advantages that we see. Okay, of course, computational requirement will be less. You don't need a lot of GPU compute to do. You're not running it twice, right? So that's also thing, simplicity, because directly into the SFT process, we are integrating the alignment directly there, and that's what it is. Okay, so understand this, right? So ORPO method uses an odds ratio. You have to understand. You have to focus on this word called words ratio. Focus on this terminology to weigh the model's output. Basically, this is all, boiling down to neural networks, guys, right? How we optimize the loss function. So what it says odds ratio to weigh the model's output, favoring those that align with the desired preferences and penalizing those that don't. So it gives a penalty, when it comes to a bad response, and this is achieved by adding a simple mathematical term to the model's loss function. Okay, which helps the model learn to distinguish between favored and disfavored outputs more efficiently. Now this is what we have explained over here in this code that you see, this part of formula. Okay, not the code, the formula that you see. I'll give this screenshot probably in the description, guys, about ORPO. Okay, and now let's come back and, see if there's a required, we'll again back to our tab and we'll explain that there's a requirement. Now heading back to our pod, okay, which is here on notebook. Now we are okay with this, guys. Okay, so what we are doing here, we have installed few things, and I have created a lot of gist earlier. That's to save some time. You can see some of the gist are over here. I'll just want to refresh this once. Cool. Now what I'm going to do next is I'm going to import. So let's import torch and multi-processing. Okay. Now I'm going to have from data sets import load data set, because we are going to load data set, because we're going to use let me make it a bit bigger, guys. Okay, so increase code font size, probably, I believe. Yeah. Now I'm saying from low data set, from Hugging Face, we're gonna use some data sets like Open, Go, and Echo and things like that. Okay, so from PEFT, parameter efficient fine tuning, LoDA config, and then PEFT model, and then we need k-bit training, and I will explain each and everything. I have a very detailed fine-tuning crash course, guys. I'll probably you should watch all of those video before watching this one. This might be a bit advanced if you have no idea of how to fine-tune LLMs. Don't watch this video if you haven't fine-tuned ever in your life previously. Okay, when it comes to LLMs. From transformers import, and here we're gonna keep a few things. Okay, so from transformers import auto model, or let me just do it in single line. Okay, so I'm gonna have auto model for causal LM. Okay, so for causal, because it's a text generation task that we're gonna do, causal LM, and then auto tokenizer, uh, auto tokenizer, and what else do we need? We need bits and bytes config. Okay, so bits and bytes config. So let's get that here, bits and bytes config, and then training args. Okay, so let's get it here. So training arguments. And if you are not someone who likes to write code along, please feel free to just skip the video and don't watch the video and just take the code directly. But if you want to learn a few things that I'll be covering while writing the code, I'll recommend you should watch the video because I keep sharing the tricks and the crucial information while I'm writing the code. Trainer. So from TRL, we are getting the ORPO trainer, which is in transformer uh, libraries TRL that we have. And now we're going to have ORPO config. So let's get that. And we are okay with our import. Now let's load let's check the CUDA and stuff first. So I have created a gist. This one. Okay, let me just come to CUDA Pi. Uh, and if you are not on 800, I will probably show that. Okay. If you are using 800, you should have flash attention probably, that supports that. Okay, so let's check that out. Now, after that, as you can see, that has been done. So I'm going to have model equals, let's call it model name rather. Okay, so model name. And we are going to use Mistral 7B, guys. So let me just show it over here. So I'm going to write Mistral AI, Mistral 7B instruct model. We're going to use the version 0.1. They have 0.2 as well, but I'm going to use this for simplicity. You can try that as well, but I'm going to use model name this. And yeah, so let me just run this. And now let's get the tokenizer. So tokenizer equals, and we're going to use auto tokenizer because you can see auto tokenizer dot from pre-trained. So let's get that. So from pre-trained, and then I'm gonna write model underscore name and then add EOS token. So let's do that. Okay, add EOS token, and I'm gonna make this true by the way. Okay, so true and use fast equals true as well. Tokenizer is done. Then we are gonna have tokenizer dot pad underscore token equals tokenizer dot EOS underscore token. And here this is important. Okay, if you are using flash attention, you can do the padding side equals left in tokenizer. If you don't have flash attention, you make it right, otherwise the model will not be at all, it will not be good at all if you make left and if you don't have compatibility with flash attention. So it's very necessary for that. Now that's what I'm going to do, tokenizer dot padding side. And if you want to understand what is padding side, you have to watch my crash course video on fine tuning. And now let's do this left. Okay, and now let's run this. And you can see we are done with this. Now let's load the dataset, guys. Okay, so I'm gonna use from Hugging Face H4, and I'll show that okay what we are going to use. So if you open Hugging Face H4, they have a data called they have a ultra feedback data. Okay, yes, this one, ultra feedback binarized. Now I'm gonna use this data. Okay, and Argila has a clean data. Probably I have to check that out. But this is the data I'm gonna use here. Okay, you can see it has let me just do that. It has a prompt and it has a chosen, rejected, and messages that you see, right? So it's very good for fine tuning an LLM when you want to align it. Okay, and that's why we're going to use this now. So what I'm going to do here next is get the data set. So let's get it a data set here, and data sets equals uh, load underscore data set, and let's pass this over here. Okay, now let's just copy. Let's just copy out here, and then I'm going to split. So split, and split is always a list. Excuse me. And when you do a split, you're going to write train underscore pref. Probably you can just give a split train underscore preferences and then test underscore prefs. Okay, and then you close the list. Prefs. Let's get this. You can see it gets the data set. Okay, and then I'm going to write a process function. So define process. Okay, row. Okay, and probably let it basically download that. Okay, meanwhile it's downloading, and what I'm gonna do is probably once it's download that, I'm probably we can take that from our gist as well. We have in our gist, so let's get that. Now let me just print the data set here once quickly. Data set, and you can find out we have all of these. So we have to process. Okay, so let's go back to our thingy here. Okay, and I'll go to all gist. And when I go to all gist, I have a process py. So I'm gonna just copy this over here. Okay, this function just to save some time. Okay, these are doing nothing but just processing. That this will help you just process the data. That's it. And yeah, ignore these warnings. You can just ignore it for now. Now let's load the model. Now I'm gonna load the model here. So for that, what I'm gonna do here next is, excuse me, it's happening. Meanwhile, let's scroll down, 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 down. Yeah, and we are good now. So you can see it's down. These are the things that we have. Let's have BNB config, guys, bits and bytes config. And in bits and bytes config, I'm going to have bits, and let me just do that. And here in bits and bytes, load in 4-bit. So I'm going to say load in underscore 4-bit. And that will be true. It's a Boolean value. So you give load in 4-bit to BNB underscore 4-bit quant, 4-bit quant. And that goes a type, and I'm going to say NF4 here. Okay, NF4. And then I'm going to write BNB again, 4-bit underscore compute D type. Okay, so compute D type, and then it's going to have torch underscore D type. What next? Excuse me, this is wrong. What next we have? Use double quant. We're going to make it true. So BNB underscore 4-bit underscore use double quant. So let me just do use underscore double quant, and I'm gonna make this as true as well. So let's make this true. And these are our BNB config. So I hope you are familiar with BNB config. Let me just run this. And we are done with the config. Now I'm going to have a model, and then I'm going to use auto model for causal LM, and then dot from pre-trained. Okay, so from pre-trained, and inside this I'm going to pass my, or let me just do like this. Okay, and then here I'm going to pass my model name equals, or let's just write model name, and then you have torch underscore D type, and you can just write torch underscore D type, and then quantization config equals BNB config. That's where we have defined on top. And then you can have a device map. If you are on a GPU, and you can see that I am on A100, I'm going to have as yes, use my one GPUs. I only have one GPU. I'm running it on one A100. And you can also write attention implementation. So I'm going to write ATN. Let me see if it can suggest me something. It's not suggesting me. I hope it's, yeah, I think it's ATN implementation. And then I'm going to write ATN implementation. Excuse me. And let me just see that. Okay, and I think we are good. And you can see it's downloading the model. It will take a bit of time to download the model, guys. Okay, but let it happen. Okay. We'll download the model, but meanwhile we will start writing the next piece of code. So I'm going to write is model equals, not model, excuse me, model. Then what we're going to do is we're going to use prepare model for k-bit training. Okay, so this is important, okay, for the memory compute. So I'm going to say prepare model for k-bit. And if you want to understand why do we use k-bit, then again you have to go and watch my first video on fine tuning, which is a crash course. Okay, so this is fine, and then we're going to configure the pad token. So for that, model.config dot pad underscore token, and then underscore id, and then I'm going to write tokenizer dot pad underscore token underscore id. This is what I'm going to do. Now let me add a few more cells here, guys. Okay, and meanwhile it's going to download all the model started weights and load the model and things like that. Okay, so let it happen. Now we're going to write a pipt config. So let's do a pipt config, and I'm going to use LoRa config for that. So let me just excuse me, the process is busy and it doesn't show me anything, which is fine. So LoRa config, and let's have a LoRa alpha. I'll keep it 16. You can keep it higher as well. Okay, LoRa underscore dropout, and I'm gonna keep this at 0.05. Okay, and rank equals 16. You can make it higher, but that will take more memory compute. And then I'm gonna write bias equals none. Pretty much just copy paste. Okay, guys, from all the tutorials, video, whatever. Task type causal LM, guys, just to define it. Okay, causal LM, causal language modeling, guys, not mask language modeling, which is MLM, where you fill a mask token. Okay, now target modules, which is really important. Okay, so in case of Mistral, we have k projection, and again I have covered all of these in details. What do you mean by k projection, upward projection, v projections, q projections, and blah blah blah. You have to invest a bit of time, guys, to understand this topic. Now v pros, and after v pros I'm gonna have o pros, and then I'm gonna have get pros, and after get pros I'm gonna have down projection, and then what else? I think upward projection is also supported here for Mistral 0.1. Okay, let me have a look at my notes. K pros, Q pros, V pros, O pros, get pros, down pros, and up pros. I think we are good. Okay, let me just do model. Let me just run this and have a pift config end. Okay, now we have our pift config. Once we have the pift config, let's train it for less epoch, like 100 epoch or something. So I'm going to go inside here, go to all gist, and I'm going to copy the config, ORPO config, and I'll explain that quickly. Now come back here in notebook. I'm going to make do eval false. It will take a lot of time if you make do eval true. Now, if you look at here, I'm saying ORPO config, so I'm using ORPO config. Okay, that's the changes I have made here, and I'm saying okay, and this is coming from TRL again, and we are using output directory evaluation strategy steps do eval, which is like false, optim, per device, blah blah blah, gradient accumulation, all of those. Like why should we use gradient accumulation? That basically distributes the GPU and things like that. When you are training it, the weights on the GPU, how it offloads it. Watch my fine tuning video, guys, for that. And then we have logging steps 20, eval steps 20, and I have only have max step as 100. Just want to show you how you can do that. Okay, save steps, and of course it will take a bit of time even if you do it on 100, because the size of data is bit big. Okay, and if you look at beta is 0.1. Beta is ORPO's lambda, by the way, the lambda hyperparameter that you have seen earlier when I was writing the mathematical formula. And I have a max length 124. You can of course make it a bit smaller as well, but this is what it is. Okay, now uh, what I'm gonna do here is, let me just run this now. ORPO config is done. Let's have a trainer. So I'm going to have trainer equals, and I'm going to use ORPO trainer. So let's use ORPO trainer, and inside this ORPO trainer, the thing that we are going to do is, so let me just, excuse me, ORPO trainer, and inside I'm going to have model equals model, and train data sets. So here you write bring all of your data. So train data sets is equal to data set, and then you make it first one and eval data sets. Okay, and eval data set equal to your data set, and then excuse me, okay, data set, and then it goes one here, data set one, pift config equals pift config, and then I'm going to have args equals orpo config, and then I'm going to have tokenizer. So tokenizer equals tokenizer, and we are good, guys. Okay, now if you look at the trainer, we are saying ORPO trainer model equals model, train data set equal to data set, and the first in the list and data set, second that we have in the eval data set, pift config is nothing but the pift config, args equals to ORPO config, and tokenizer equals tokenizer. And you can see it's running right now. It'll take a bit of time. And once that is done, then you can start the training by trainer.train. Okay, you can see its map, so it has to map to the entire data that we have. It's 60,000 odd that we have rows in that. Okay, so let's wait for that. Okay, and we are after that we're gonna just do trainer.train, guys, to start the training. And probably I have to pause the video because it will take a bit of time to train it. Okay, and so I'm not doing any evaluation. If you do eval, it will take uh it takes a lot of time. For 100 steps it might take around, so uh for one checkpoint it takes almost 2 hours, for when you enable the evaluation. And that's why, if but I recommend that, because if you are focusing on to fine tune, and of course you need an evaluation benchmark, because you have to probably publish your results on a leaderboard, and then you should do that. Okay, so let me just pause the video, guys. It takes a bit of time to map that. Okay, I'll come back once that is done. So as you can see, I have started the training here using trainer.train. But I have did a bit of changes just to save a bit of time and also save the compute, because I am low on compute on Runpod. So what I did, I ran this on only 20 steps just to show you, and I also did the eval part that you currently see it's running. So if you look at over here, after that I did trainer.train, and it says currently training with a batch size of 2. All these hyperparameters that you see can be tweaked according to how much compute you have, and also depending on the data size that you have. So if you look at here, I only did it for 20 steps, which is not feasible at all. At least you have to do it for 1,000 steps and even more than that, okay, to get a good performance. Now it says running evaluation, number of examples 2000, batch size 2. You can see it's giving you time that it's doing 0.38 iterations per second. Okay, so it's right now in the evaluation, and you can see the steps has been completed. Once it completes the 1001, you will see the validations, loss, and everything over there. Now, I'll recommend that you train it for more epochs, more steps, and you can also do it for minimum is one epoch, but you can also do it for two epochs. Okay, if you have the compute power. I'm running this on A100, guys, and I'm a bit of short on compute, and that's why I did only on 20 steps just to show that. And we have a results folder. When you click on this, there's nothing right now inside it because it's still running. Once you have that checkpoints will be saved inside the results folder over here. Now, if you look at here, our training has been completed. It says training completed, and it says do not forget to share your model on huggingface.co/models. Now, if you look at here, the training loss is 2.12. Okay, it took that much amount of time, and train loss, we have it over here. Now, if you look at training loss, right, 2.12, you have to bring it down even less than one, right? Something around 0.5 or something. Now, we did only for 20 steps, which is nothing, which is not at all a good, not at all an optimal steps to train that. You have to probably train beyond 1,000, at least to start seeing a bit of generalization on the model. So model will start generalizing, right? So you have to do that. But I'll share this code. You can see the training loss and the validation loss. It will start coming down if you do it for more step. Pretty sure, I'm sure on that. Then you see rewards chosen, rewards rejected. So if you look at the chosen and the rejected, not much of difference as of now for this one. Okay, rewards accuracy per accuracies, which is like 0.57. Rewards per margin, that is fine. Okay, now let me see log odds chosen. This is where you look at log odds ratio, the formula that I was showing on the screen previously. Now, this is a great way of, training or aligning, rather with the right word, aligning the LLMs using the ORPO that we have, the alignment technique or the methods. Now, what we also doing here, guys, I'm showing you that how you can push the model now back to Hugging Face so you can use it later on. Now, of course, I will delete this API key. Now, what we are doing, we are using Hugging Face API to basically push the aligned model, the Mistral 7B chat model that we have basically, aligned here, and we are just pushing it to our Hugging Face repository. Now, if you look at here, this is my username. This is the model name that I'm giving a name called Mistral 7B ORPO, and Hugging Face API. I'm giving my access token, which has a right privilege to write the model back to Hugging Face, and then I'm using create repo. Now, using this API, this is a high level API for Hugging Face that basically creates a repo. You can see this is the repo, and you can create two types of repo. One is for dataset, the other is for model. If you want to push a dataset using this module, you have to write dataset here, but I am pushing a model back, so that's why I'm writing model. And you can see the repo has been created, and then I'm saying upload folder. So which folder? The results folder that you have. Don't give the results slash checkpoint 20, just the results. It will automatically take the checkpoints over there and uploads everything. So if you look at inside checkpoint, we have all these files. Okay, now it uploads everything which is there. Okay, now if you come back and you can see this is the model that the original model, and this is my GitHub repository, excuse me, Hugging Face repository. When I go here, you can find out in files and version there is a checkpoint 20. If you go inside it, these are all the models that we have. Okay, you can also again, from here also you can move this, okay, out of this checkpoint 20 if you want. Now you can see all the these are all aligned model that we have. This is your safe tensor adapter model dot safe tensor. You can again merge the adapters with LoRa if you want to do that. I haven't done it yet, but I leave up to you to try it out. And here we have the PT, which is the PyTorch one. So you can see LFS means these are the large file, from GitHub, and this is what it is, guys. So now you can see that we have pushed our model back to Hugging Face. You can do a bit of customization over here. You can come out of checkpoint 20 and you can again inference it, but that's a very redundant task to do that. Okay, so maybe you can try it out and let us know. Now, this notebook will be available on my GitHub repository. Feel free to fork or clone it and try to extend this for your LLMs that you have. If you want to do it for more steps that I recommend, and let us know your findings. This concludes our experimentation with ORPO, guys, and how you can align an LLM with ORPO. That's all for this video, guys. I hope you got a bit of understanding of ORPO, and how to use ORPO to basically, perform performance alignment or align the LLMs, and how you can use this to basically fine tune on your data or any custom data that you have. And how ORPO can also be used as or can be looked as an alternative to DPO, IPO, or KTO kind of alignment methods that we have. The notebook will be available on my GitHub repository. I'll give the link in description. If you have any questions, thoughts, feedbacks on how to use these performance alignment techniques or methods in your experimentation, feel free to ask me in the comment box. You can also reach out to me through my social media channels. Find those information on channel banner and channel about us. Uh, if you like the content I'm creating, please hit the like icon. And if you haven't subscribed the channel yet, please do subscribe the channel, guys. That motivates me to create more such videos in near future. Share the video and channel with your friends and to peer. Thank you so much for watching. See you in the next one.